we're going to talk about the use of hyperspectral data for coastal and ocean systems. Before we talk about hyperspectral data in general, I wanted to point out some aspects about the photosynthetic apparatus or photosynthetic organisms, and particularly talk a little bit about the different pigments or compounds that absorb within the visible range. First, as most of you know, most photosynthetic organisms, they have chlorophylls. Depending on the organism, they may have chlorophyll A, B, C, C2, etc. And these are the main components of the photosynthetic apparatus. Most of here on the right, we see a graph where some of these pigments absorb. You see that the chlorophylls in particular, they usually absorb in the blue and the red region of the spectrum. This is why, for instance, we see the plants, most plants are green. Now, there are other pigments also associated with some photosynthetic organisms, and here are some examples of them. Phycobilisons, for instance, they absorb in completely different regions of the spectrums. Phycoerythrin is a pigment that is characteristic of red algae, and it absorbs within the blue, mid-blue, to about the yellowish or orange part of the spectrum. And eventually, this is why we see red algae as red, because it emits on the red. And then phycocyanin, it's a pigment that is characteristic of cyanobacteria. And phycocyanin, as you see here in the graph, absorbs mostly on the green to red part of the spectrum. Now, both of these pigments, they work as like harvesting antennas in the photosynthetic apparatus. And as I said, they capture photons between the green and the red part of the spectrum, some of them. Then there are other pigments associated with photosynthetic organisms are the carotenes, which are mostly for photoprotection. And some of them are the carotenoids like pyridinine, which is characteristic of corals, zooxanthellae inside the corals, beta-carotene and others. And there are xanthophylls like diadenosantine and zeaxanthin, which also help in photoprotection as well. So you see here in the graph where typically where most of these pigments absorb in the visible range, and this is going to be key eventually for translating this information into the hyperspectral data when it's collected by different sensors. Now let's take a look at how in situ data collected with a handheld spectroradiometer, in this case a GER 1500 that has 512 spectral bands with a nominal bandwidth of approximately 1.5 nanometers, it shows differences in the visible spectrum between four typical coral reef components, in this case of the Caribbean. For example, we have Poraides astroioides, which is a mustard-head coral, an organism which is also a relative of corals, Palitoa calibaerum, a zoantid. And then for comparison purposes, also I included here data from red mangroves and also turtle grass, seagrass as well. This is some of my data. It's not published, but it's all of mostly for just for showing the different spectra of these data of these organisms and how they show in a spectrum. The differences here in multiple regions of the spectrum between these reef components can easily be seen with this type of data, and it shows the advantage of having many data points through the spectrum instead of having 3 to 4 discrete points, which would be the case for multispectral data. Now here's again, Amber went through some of these in the first session, but it's always it's a good thing to go back again and kind of refresh our memories. The differences, some of the differences between hyperspectral and multispectral sensors. The multispectral sensors have been the norm with satellite sensors in particular, but they are limited by the number of spectral bands that can be used. On the other hand, they have there's the advantage to some of these missions of the longevity of the data sets associated with them. When you think about the Landsat series, for instance, it's been around since about 1972. And the MODIS series, both in Aqua and Terra, they've been around since late 1990s or early 2000. And also, they have a fairly high temporal resolution on the order of days to weeks. In the case of Landsat, is every 16 days. In the case of MODIS, every 1 to 2 days also. So there's a lot of data associated with multispectral sensors that can be used for both land and coastal and ocean systems. On the other hand, hyperspectral data, so far, there are very limited number of satellite-based sensors that are hyperspectral. We have talked a little bit about Hyperion, which was on board the EO1 spacecraft. And data from Hyperion is available from the year 2000 to about 2017, when it was decommissioned. Now, Hyperion had a 30 meter spatial resolution and 220 bands at 10 nanometers. There are some that are mission specific. For instance, the HICO, the Hyperspectral Imager for the Coastal Ocean, which was on board of the International Space Station. And there's limited data available for HICO, but HICO, one of the most important things is that HICO was specifically designed for coastal oceans. But there's only about 5 years of data from HICO and for specific areas also, because it was it collected data on a request-based basis. Now, there are hyperspectral sensors that are airborne, and we also mentioned AVIS, the Airborne Visible Infrared Imaging Spectrometer. There's a new version of AVIS called the AVIS New Generation, or AVIS NG, and also the PRISM spectrometer, the Portable Remote Imaging Spectrometer, that has also been flown in some missions, particularly some missions related to the coastal ecosystems. Now, lately, there's been the development also of hyperspectral cameras, particularly for unmanned airborne systems or drones. That it looks promising, but there's still a lot of road to cover there, and it's still a work in progress. Now, Amber mentioned in particular during the first session a couple of upcoming designated deliverables and additional satellite-based sensors, particularly two that are also related to not only to land-based but oceans or coastal systems, the Plankton Aerosol Cloud and Ocean Ecosystem, or PACE, and also the Surface Biology and Geology, or SBG. Okay, so here we have the same graph that we saw on the left-hand side we saw a couple of slides ago, where the data collected in situ with a spectroradiometer, and then on the right-hand side is the same data set but adjusted to the 4 Landsat 8 bands in the visible range, and you see that most of the spectral features that appear obvious to distinguish, particularly these reef components that we mentioned before in the hyperspectral in situ data, are lost in multispectral adjusted data. So obviously, this is just for illustrative purposes, but at least you can see here how different the data might look between hyperspectral on the left-hand side and multispectral on the right-hand side from exactly the same targets. Now, there are some considerations when processing hyperspectral data that we have to go through. And for instance, even adjacent bands can give you completely different results. So it is important particularly to do an iterative process to choose which band is the appropriate one depending on the target. Now, also, typical atmospheric correction algorithms might need to be modified accordingly depending on the sensor. most times people still use some of the typical atmospheric correction algorithms like Flash or Tafka or ATREM or others, but still you might need to tweak a little bit there just to make it more feasible to be used with hyperspectral data. And for some sensors, there might be some additional geo-rectification that might be required depending on the sensor. So for example, for HYCO, speaking about coastal ocean, for HYCO, multiple images of the same target do not necessarily always cover the same identical spatial coordinates. And images of the same area are acquired at different times during the day, or even at different angles due to the ISS orbit and repositioning. So you might need to do some additional geo-rectification there for make the images useful. Also, there's the uncertainty with overpass predictions that affects for instance, the deployment of field crews for vicarious data collection, chips, and others, and this is usually pretty costly. Similarly, for airborne sensors such as AVIRIS or PRISM, the field campaigns are usually costly. We're talking probably on the order of maybe more than a couple $100,000 for a field campaign. So that's something that you have to take into consideration particularly when designing the project or budgeting for the project. And also there are the typical aircraft issues, for instance, pitch, roll, and yaw, that affect the image acquisition and might require additional processing as well. Now, unfortunately, due to the usual complexity of coastal waters, even with hyperspectral imagery, benthic classification in particular can be extremely challenging, and it's still limited to the first tens of meters of depth, even in the clearest waters, for example, in tropical islands, such as the image that you're seeing here on the right. Now, different regions of the visible spectrum are rapidly attenuated in the first meters, particularly in the red. And the same thing, even more dramatically, happens with the near infrared and UV regions as well. Now, the characterization of deeper communities is usually only restricted to the use of alternate means, such as sonars or autonomous underwater vehicles with camera systems, because of the limitations of airborne or satellite-based remote sensing imagery. Now let's see some examples where hyperspectral data has been used for storing coastal or ocean systems. Here's an hyperspectral image collected in Puerto Rico back in 2004 in an area known as La Palguera in the southwest coast of Puerto Rico, before the massive coral bleaching event of 2005. You can see that even in this image at 4 meters spatial scale, features such as seagrass beds, which in the mid-bottom graph here, and sand also are barely distinguishable without any atmospheric correction, despite the shallowness of the reef lagoon, which is in this case about 1 to 2 meters deep only. Also, in very shallow waters, there's an influence of the short water column that it's surrounding the bottom surfaces. Now, in this case, the University of Puerto Rico, particularly the Bioptical Oceanography Lab team, they used black and white waterproof tarps that they located in different parts of the reef there, and then they collected spectral data with the same spectral radiometer that I mentioned before, the GER 1500, for water column correction here. This is a very tedious task, and it took a lot of manpower hours to do it. Now, here we show the agreement between the average data and the field collected spectral curves. particularly in the red region, where we can see the absorption of microscopic organisms that are still in between the grains of sand. Changes in the water column composition can cause the differences that we see here between AVRIS and the in situ data. And also the AVRIS sensor was not specifically designed for underwater targets. This might also be the case of some of these, or the reason of some of these changes or differences between the in situ data and the AVRIS data. Now, after atmospheric and water column correction, the spectral signatures collected by both AVRIS and the in situ spectroradiometer are much more similar to each other. Other differences, such as those associated with the smoothness of the curves, are also associated with the bandwidth differences between both sensors. Remember that for AVRIS, H band is 10 nanometers, versus for the GER 1500 it's about 1.5 nanometers. So the GER has a more smooth curve. But in general, many spectral features are maintained, as you can see here in these different graphs. Now, during session 1, Amber briefly mentioned the NASA-funded Earth Venture Coral mission. Coral stands for the Coral Reef Airborne Laboratory. The goal of Coral was to provide critical data and new models needed to analyze the status of coral reefs and to predict their future. Now, Coral provided the most extensive pictures to date on the condition of a large portion of the world's coral reef from a uniform data set. The spectral resolution for Coral was from about 350 to about 1053 nanometers, with bands that were sampled at around 3.5 nanometers with the PRISM radiometer. Coral, like I said, acquired airborne spectral image data using the portable remote imaging spectrometer, or PRISM instrument, which was installed in a commercial airplane, a G4. And concomitant with the flights, in situ data were collected to validate the remote observations. Now, for each reef, the spectral image data were processed to provide reef condition described by measurable quantities of benthic cover of coral, algae, and sand. And then they use additional algorithms to calculate primary productivity and calcification. These three these parameters were analyzed quantitatively against these about 10 different key biogeophysical parameters using different models and different algorithms to understand the reef conditions today and to predict the reef conditions for the future. In the case of coral, for each square kilometer of reef, it generated about 10,000 observations on benthic cover, primary productivity, and calcification. Between 2016 and 2017, Coral flew over key reef areas in the Pacific Ocean, including Hawaii, the Mariana Islands, Palau, and the Great Barrier Reef, as you can see from this survey on the map on the left. On the right, you can see a coral image from the Northwest Hawaii, where the hyperspectral data was used to create classification to map the locations, particularly of coral, algae, and sand. Now, the Coral Research Group conducted a series of field campaigns at the study sites in the Pacific, which included the collection of spectral libraries from the main reef benthic components, in-water characterization of apparent and inherent optical properties, diver-operated video transects collection for benthic cover analysis, and measurements of primary productivity with in situ data loggers. All these data were used for calibration and validation of the PRISM images, which in turn were used for benthic mapping at the reef, island, and regional levels, as well as estimation, like I said, of primary productivity and calcification at different levels. Now, previously, we saw a graph with some reef benthic components and their spectral similarities or differences, as well as some of the data collected by the Coral project team. In a recent paper by Tom Bell and colleagues, including some of the co-authors of the Coral team, they simulated the ability of a spaceborne hyperspectral sensor to accurately map the fractional cover of coral reef benthic classes under different water quality conditions and depths using a semi-analytical process, the hydrolyte radiative transfer model, and a multiple end-member spectral mixture analysis, or MESMA, to estimate cover. They obtained best results for shallow waters of less than 3 meters depth for most typical reef reef quality conditions, and a proposal that at a depth of more than 5 meters should only be classified only under low chlorophyll and sediment concentrations. In short, MESMA uses multiple class-specific representative spectral signatures to model each image pixel and to determine the optical combination of each end-member spectral signature and fractions. The technique was developed and tested with average data originally by Roberts in the late 1990s for mapping chaparral environments, but has also been applied to kelps and reef environments by Dr. Bell and Dr. Cavanaugh's group from UCLA for a while already. In the paper, the authors also pointed out the potential advantages of having new hyperspectral satellite-based systems such as SVG or PACE for assessing reef changes at multiple spectral and temporal scales. Now here's a reminder of some of the characteristics of HYCO, since it was particularly designed for coastal systems. HYCO was used to sample specific coastal regions at 90 to 100 meters with a spatial resolution, with a spectral coverage from 380 to 960 nanometers, with bands that were sampled every 5.7 nanometers. The sensor had a very high signal-to-noise ratio that it is indeed useful to resolve the complexity of the coastal ocean. As a demonstrative instrument, HYCO was designed to collect only 150 times 200 kilometers scene per orbit. The regions to be collected were determined weekly by a scheduling team, and the focus was on providing HYCO data for scientific research of coastal zones and other regions around the world. HYCO demonstrates coastal products including water clarity, bottom types, bathymetry, and onshore vegetation maps. During its 5-year in operation, HYCO collected over 10,000 scenes from around the world. And this is this is something that we showed also on the during the first session, but I thought it was appropriate to re-show it here because it's a particularly cool animation product developed by the Goddard researchers. Here in this animation, this was a series of images that were particularly collected over Bermuda in August 17 and 2013, and it cycles through all 128 HYCO channels, displaying 3 at any particular time. Now, the sliders on the right show which channels are represented by their central wavelengths in nanometers were used for the red, green, and blue components of each frame of the animation. Now, the image doesn't have any additional processing of top of the atmosphere radiances in this case, but it shows how you can choose between different bands, relatively similar bands, but it shows very different products. So it allows you to see how different bands highlight the various components of the island ecosystem, from land, shallow water, or coral components. Now, quite frequently, seagrass meadows represent a mix of seagrasses and macroalgae, mostly brown algae. The spectral limitations of multispectral data do not often provide for the differentiation of these shallow water benthic components. Now, Cho et al. In a series of papers in 2013 and 2014, they studied the use of HYCO data in particular for distinguishing between seagrass and macroalgae areas dominated in Florida, the Florida Keys. The authors found that the HYCO bands, particularly in between 665 and 675 and 708 and 713 nanometers regions, can be used to distinguish seagrass from macroalgae and propose the use of two benthic classification methods, namely the slope red and the slope near infrared for this purpose. And the models were compared to other existing classification models, such as the spectral angle mapping or SAM, or typical unsupervised ISO data classification processes. Their models outperform both SAM and ISO data processes, particularly in the very shallow waters, with an average of 65% accuracy. Now, similarly, on a more recent paper by Heidi Diersen et al. In 2019, they used 1 meter spatial resolution hyperspectral data obtained with PRISM to map shallow and moderately deep eelgrass beds in the tidal embayment of Elkhorn Slough in Monterey Bay in California. Their group combined the hyperspectral data with a semi-analytical inversion model named HOPE, or Hyperspectral Optimization Processing Exemplar, to characterize water column parameters and to show subtle differences in the spectral shape and differentiate between different types of submerged vegetation. Particularly, we can see the improvement in the benthic reflectance retrieval in the bottom right-hand figures here, and the agreement collected with diver collected benthic cover data shown by the different color dots. Now, the distinction between coastal plant species like mangrove forests still need a lot of research. Here's some in situ data that I collected in Southwest Puerto Rico 2 years ago, still in process. And it shows how similar the four mangrove species of the Caribbean can be spectrally, in particularly here in the left-hand figure. Still, to some extent, areas heavily impacted by, let's say, disease or a heavy drought period might be more moderately spectrally different if their canopies are, uniformly impacted. Now, also, I wanted to remind you again that last year we conducted a SART training, which included one whole session on mangrove forest mapping and monitoring, as well as this past November. And in November, there was another full training on remote sensing for mangroves in support of the UN Sustainable Development Goals. So I encourage you guys to watch some of those if you want some more additional information of how to process data for mangrove analysis in particular. But anyway, mangrove ecosystems, as we know, they protect the coastlines from erosion and increase the water quality also surrounding them. Now, continuous monitoring of mangroves is necessary to assess the impacts of sea level rise, for instance, and increasing salinity. Each species of the mangrove forest, in this case in the Lothian Island, has a different threshold for these environmental parameters. So understanding the composition is important for conservation efforts. Here's a study by Harry et al., a recent study until 2020, that used average NG data, airborne data, in the hopes of creating a species-level vegetation classification in the Lothian Island in the east coast of India. In addition to hyperspectral data, they also examined multispectral data to compare the target capability of specific vegetation type classifications. Data was analyzed from the Landsat OLI and Sentinel-2, also as well with Hyperion and the AVERS-NG data. Now, Landsat and Sentinel perform similarly, but with more spectral information rendered by the hyperspectral data. Hyperion and AVERS perform much better at more specific classifications and receive higher accuracy scores also. The AVERS-NG performed the best and was able to provide many more species-level classifications. Now, this is what we should expect from a hyperspectral remote sensor. The more bands available to capture reflectance, the easier it should be to distinguish between different vegetation types. Performance of AVERS in this case is particularly notable given how complex the environment in this location is. However, it is important to note that AVERS-NG also has the highest spatial resolution of any of the other sensors that were used for this study, which also contributed to the accuracy as well. Algal blooms can and cannot be toxic depending on the organisms that bloom. Hyperspectral data can be particularly useful for detecting specific types of bloom and therefore for monitoring coastal and ocean waters prone to the development of these. Here's an example of a not necessarily harmful algal or plankton bloom. In this case, we see the detection of a bloom of a globally distributed non-toxic ciliate known as Mesodinium rubrum. The ciliate produce intense red-colored blooms, and here on the left-hand side, a modest image from 2012 shows an elevated chlorophyll A fluorescence patch, but due to the limited availability of visible bands of immodis, the type of bloom cannot be distinguished compared to and here we can compare it to an image of Hyco on the same day that shows the typical yellow fluorescence of phycoerythrin, which is the main pigment in this particular case. The middle photos here show how the Mesodinium bloom looks like from above, and below here is a microscopic photograph of the organism. Mesodinium is a mixotrophic as it enslaves chloroplast from its main food source, which is a microscopic algae, but can also engulf and process other microscopic organisms of the planktonic community. The graphs here on the right-hand side compare the remote sensory reflectance of MODIS and Hyco and show how the Hyco data reveals many peaks and dips related to the presence of phycoerythrin, particularly the peak that is characteristic around 565 nanometers, which cannot be detected by the MODIS data. The bottom graph shows the pigment absorption features. Here's a yellow fluorescence peak. The bottom graph shows the pigment absorption features of these organism pigments and includes chlorophylls and other pigments like alloxanthin and phycoerythrin. Here for reference is the AS as an PE on the graph in the legend, respectively. And this is data from Heidi Diersen and also et al. From 2015. Now here's data collected by Bernaldo et al. And published a few years ago that shows the same concept, but in this case in regards to the concentration of total suspended matter in a reservoir in Brazil. The graphs on the top are the in situ hyperspectral data collected with a spectrophotometer, and on the bottom graphs show the spectral information collected by Landsat OLI for the same waypoints and the same date. In this case, the lack of bands in the near infrared, particularly between 700 and 850 nanometers, does not allow for the use of several spectral features to discriminate between the different sites. And you see here the differences, particularly between 700 and 800 nanometers, which you cannot see with the Landsat data. Now, hyperspectral sensors such as HICO and the proposed SBG with a fairly high spatial resolution, just let's say 60 to 90 meters, have and will provide respectively the opportunity to characterize a wide range of watercolor constituents in great detail, as shown by the high correlation in the Keith et al. 2014 paper from chlorophyll A estimates in the northwest coast of Florida. Hyperspectral data can be successfully compared to classic studies performed with multispectral sensors and similar or higher spatial resolutions. In this example, the authors use an iterative process using remote sensing reflectance values from the HICO bands, particularly bands 45 to 61 at 657 to 749 nanometers, to assess which bands were most efficient for the retrieval of diverse water quality parameters, including chlorophyll A, CDOM, and turbidity or suspended particulate matter, based on the sensitivity of the different wavelengths to these constituents. Similar processes have already been applied to multispectral data from MODIS and MEDIS for about a decade or more already, but in this case, the authors took the advantage of the narrow bands of HICO to come up with a more sensitive algorithm specific for each of these constituents. Now, I will leave you with my colleague, Zach Benston, who will provide you with a short demo on how to acquire hyperspectral data for coastal and ocean systems, and some standard processing that can be performed with typical remote sensing or GIS software. Back to you, Zach.
Hello, everyone. As Juan mentioned, I'll be walking you through our data access and display demonstration today. But first, I want to go over some background information before we get started. So one of the most useful and comprehensive websites for accessing coastal and ocean remote sensing data is the NASA Ocean Color Web data browser. So I'll be going through how to use Ocean Color Web to explore and access data later in the demo. But I just wanted to mention that this website doesn't just include hyperspectral data. It also includes data from multispectral sensors, and that's things like MODIS and VIIRS. And so the data browsers available on Ocean Color Web allow you to search data products at various processing levels, and you can also specify a lot of search criteria to narrow down your search results. These search criteria include things like data product type, chosen sensor, spatial extent, and date range. You'll also be able to preview the data to visually inspect for quality and completeness of imagery, which includes checking for things like cloud cover that might end up obstructing your imagery and making it not analysis ready. And for cloud cover, we typically suggest using data with no more than 20% or so cloud cover. So the link to Ocean Color Web is provided here on the slide for you to try out some of the data browsers after the demo. And to download data from the browser, you'll need to register for a NASA Earth Data account. You'll be prompted to create that account or log in if you attempt to download data from the Ocean Color Web browser. But the link is also provided here for you to the registration page if you want to do that beforehand. And this registration is typically pretty quick, and you'll just need an email to complete the process. So not a whole lot of information on your end. And once registered, you'll be able to directly download data from the browser. And so in today's demo, we'll be using data from the Hyperspectral Imager for the Coastal Ocean, or HICO mission, that we've talked a little bit about in this session and the first session of our hyperspectral trainings. And HICO was mounted on the International Space Station and was the first spaceborne sensor designed to sample the coastal ocean. HICO was in operation from 2009 to 2014, and data were collected over 128 bands ranging from 380 to 960 nanometers with a 5.7 meter bandwidth in a variety of oceanic, coastal, and freshwater areas around the world. So HICO's spatial resolution is 90 meters with a standard scene width of 42 kilometers and a standard scene length of 192 kilometers. The full HICO data archive is available online through NASA Ocean Color web browser, and that's kind of what we're going to be going over in this data access demo. So HICO data are readily available at 2 processing levels through Ocean Color Web. And as you likely remember from the last session, a higher processing level indicates greater pre-processing conducted on the imagery prior to your downloading it. And in the case of HICO, level 1B products have undergone radiometric correction, geolocation, and some additional corrections to eliminate image artifacts. This data product provides radiance values, and in order to make the data ready for analysis and for the processing, atmospheric correction must take place to provide surface reflectance values that filter out the effects of the atmosphere. Fortunately for HICO, all level 2 products available through this online platform have been run through an atmospheric correction model and contain surface reflectance values. This is really nice because it means you won't have to worry about atmospheric correction with HICO data. So level 2 data files also include raster layers, which display common assessments of chlorophyll A and light attenuation, which provides a metric for turbidity. So working with HICO NetCDF files is easiest using CDAS. This is the software that we're going to be using for the demo, but I just want you all to remember that you don't need to download CDAS right now. You don't need to follow along or anything like that. I'm just going to be quickly showing you some of the basic functionalities here on my screen, and then if you'd like to explore it later, you can definitely do that. So CDAS is a free and comprehensive software package developed by NASA for processing and analyzing remote sensing Earth data. And CDAS brings together a variety of processing components into an easy to navigate graphical user interface, which is really nice because it means you can kind of just point and click your way through the data rather than bringing together a lot of the tools that CDAS does. So the link to download CDAS is here on the slide. And CDAS can be downloaded in Mac, Windows, and Linux machines, so you shouldn't be limited by whichever computer you have. So within CDAS, you can easily open data products from a variety of NASA sensors, reproject data, export data as new file types, manipulate bands, and visualize data. Particularly relevant to this training, you can display spectral information of each pixel and apply algorithms to derive things like water quality and classify physical features like bottom reflectance and bathymetry. So now that you're a little bit more familiar with the tools that we're going to be using, I'll go ahead and move on to the demonstration. All right, so hopefully on my screen you can see the Ocean Color Web website. This is available through the link that I provided on one of the previous slides, but I'm going to go ahead and walk you through kind of getting to that level 1 and 2 data browser that we'll be using for HICO. So you'll just need to navigate here to the data browsers. Like I mentioned, we're using the level 1 and 2 data browsers. Sometimes these things take a little bit of time to load, but once you've clicked that link, you'll be taken here to the user interface to access kind of a variety of ocean-related data. So as you can see, there's a lot of options here for the types of data that you could potentially use. One of the defaults for this data browser is Modis. It will go ahead and just show you that data kind of here on this example screen of what data is available. But we're going to go ahead and unclick that and go ahead and click here for our HICO data, which is what we're really interested in. That's kind of how you filter by sensor here in Ocean Color Web. And then we're going to go here to reconfigure page. And that will just kind of reload everything to make it specific for HICO. It's nice because it shows you kind of all of the places where there's HICO data available. Here in this map, all of the red sections are HICO overpasses. So we'll zoom in a little bit there so you can take a look. And you can do a lot of clicking through here if you're not necessarily looking for a specific area, you just want to explore the data. This is a really nice opportunity to kind of click through and see what's available. And if you're just looking for a quick reference to see if there's data available in a specific country or a specific coastal area, this is kind of a nice way to do that. You can also do things like filtering for date, filtering specific months, specific years, and you can do that with some of the links here. As I mentioned, that's kind of whichever dates you're interested in. That doesn't necessarily line up super well with spatial extent all the time. You can definitely see what data is available on specific days. But I think for the use of this website, it's probably better to start filtering by spatial extent, just because you're not necessarily going to see a lot of repeat data for every spatial extent. So we'll go ahead and pick an area here in the navigator. There are some typically searched areas available here that you can scroll through. You can also specify your study area here just with your lat long values to get data within whatever spatial extent you're interested in. But we're going to go ahead and navigate to the Maldives. So go ahead and select that here. That's just the general area that we're going to be searching, and you can click here to find swaths. And so a lot of this data, since it's already available in the level 2 format, it will have certain algorithms kind of pre-run on it for your own use. This is currently displaying a classically used chlorophyll algorithm over the data. Not necessarily the most informative when you're kind of just filtering through data, looking to kind of sort through things. So you can go up here to toggle to true color images. So this will give you kind of a quasi true color image that you can navigate through. It provides things like dates. You can click any of these links for metadata. It shows you the spatial reference there down on this globe. And we're going to wait a second for it to download. These previews are really nice, just to kind of get a picture of what's available with the data. As you can see in quite a few of these images, there's a lot of cloud cover. So we're going to go ahead and select the one that has the least cloud cover. Like I mentioned, ideally below 20% cloud cover. And we're going to go ahead and click on that. And that's from October 14th, 2010. And so it'll go ahead and show you two previews of that data. The first is chlorophyll. That's popped up here. So it shows you kind of that typical chlorophyll algorithm applied to the imagery available in the study area. So that's kind of a useful metric. It's not necessarily calibrated to the specific study area that you're working with, but it's nice to kind of have those pre-processed kind of water quality parameters already ready to go. And then you'll also be able to see here the quasi-true color image that I mentioned. You can go ahead and do another visual inspection of that, a little bit more zoomed in. And as we can see, this image is pretty free of cloud cover, a little cloud cover down here, but certain parts of the image are definitely a little bit better than others. And how you download data from this platform. So we've kind of selected this as our chosen HYCO scene. As you can go ahead and go up here. These two links will provide for you either the level 1B data product. So that's the level 1 product, that's radiance values. And then you also have this level 2 product here, which is atmospherically corrected and provides those surface reflectance values that we really, really want. So we'll go ahead and click on that. And this is kind of where your Earth data login comes into play. I already have my account logged in. And so it will redirect you to this Earth data login page and then automatically download that netcdf file for you. And I don't think I mentioned this before, but all data available for HYCO is in netcdf format, which is really helpful when we're working with CDAS. It's already loaded with the processing and display data that we need to view this imagery in kind of the easiest way possible. So that's why we're using CDAS for this session. And so as you can see, it takes a little bit of time to download. But I will go ahead and toggle us to CDAS so that we can go ahead and get started looking at this imagery. All right, so now that we're here in CDAS, you can see kind of the graphical user interface here. One thing I just wanted to mention is that when you first download CDAS, you're going to want to make sure that you have all of the data processors downloaded that you'll be using for data. So for example, you can go up here to the OCSSW tab, and then you just want to make sure that you're selecting any sensor mission data points that you'll be working with. So in our case, we would want to click HYCO. I've already done this, so I'm not going to run it or apply any of the data processors. But this is just something that you'll need to do so that you can go ahead and start immediately working with the HYCO data. And I also just want to mention that this is something that's going to look a little bit different depending on what version you have. So this is the Mac version of CDAS. So it's going to look a little bit different from the, the Windows version as well as the Linux version. I believe that the Windows version is a little bit more complicated. You might not necessarily have this graphical way of kind of downloading these data drivers, but in the link that we provided in the slides to the CDAS download, you'll see some instructions there for how to do that for Windows. So I'm going to go ahead and cancel this since I've already done that. And we'll go ahead and import the data point that we downloaded from Ocean Color Web. And so this just immediately goes to my downloads folder. I'm going to select the netcdf file that I downloaded for the Maldives, and I'm just going to go ahead and open the product. Awesome. So you'll see here, one really nice thing about CDAS is that it kind of lays out everything that's in that file for you. So what we're particularly interested in is the metadata and the rasters that are available through the netcdf. So I just want to go ahead and toggle through some of this metadata. So as you can see, there are some options here for looking at when the image was captured, what date the image was captured, kind of the data source, what the processing level is, kind of a full gambit of metadata that you might need to describe this data, which is something that's really nice to kind of have right here in front of you. And you can kind of scroll through these, kind of get more acquainted with the data. You might be familiar with some of this from Ocean Color Web when you're looking at different data products. But this is just a nice listing for the specific metadata of the product that you downloaded. And you can also go here to look at band attributes. And this is just a basic listing of the wavelengths that are available through HICO within this data product. And as you can see, it kind of follows that pattern of 5.7 nanometer bandwidth that we had mentioned with HICO, and then a variety of bands on top of that. So we'll navigate away from metadata here, and then we'll start looking at the raster products that are available. What we're the most interested in here is this surface reflectance RRS. But I also wanted to just point out some of the data products that will come with this netcdf file. So you'll see here, this is just kind of a classic chlorophyll algorithm that's been applied to the image that we downloaded. And this displays kind of that classical algorithm that's used to calculate chlorophyll A. And you can see some of the variation there. Same goes for KD490, which is a metric for light attenuation. And you can just go through and click on each of these. A double click will go ahead and display it in CDAS so that you can explore some of these layers that are available. And KD490 is a really good metric for turbidity as well. But we're not necessarily going to focus too much on these pre-processed data layers in this demo. So we're going to look here at the available bands. There's quite a few, as I mentioned. But what we're going to do is create an RGB imagery, kind of similar to the last session in session 2 when we created that RGB image. So as you see, we have a lot of choices here for wavelengths. And we're going to go up here to the 3 raster band to create a RGB image tool. And so I already have a profile saved here, but when you go into this Create RGB Image tool, you're going to want to go ahead and select bands, and it will have a drop-down menu. One nice thing about this is it automatically displays the wavelengths that are available, and you'll just scroll through and choose whichever ones you would like to use for your RGB image. HICO is really nice because they have recommended wavelengths for an RGB image, which in this case will be 639 nanometers for red, 553 nanometers for green, and 461 nanometers for blue. So those are just the bands that are suggested through the HICO website to create that RGB image. And so once you make those selections, if this is a new profile, you're going to want to make sure to click Save here. And you can just go ahead and give that a name, and then it will just save automatically in an RGB image profile file folder. But we're not going to do that because I already have this one saved. I just named it HICO RGB, and we're going to go ahead and run that. So as you'll see here, we have a little bit better of a true color image as compared to some of those other layers that are made available within the netcdf. This is pretty much as close to a true color image as you're going to get with the HICO data. And as you can see, it shows a lot of the oceanic area around the Maldives. It shows some of the atolls. So we've got a nice mixture here of open water, shallow water with some benthic features, and then also some above water features as well. And so we're going to use the spectrum view tool. And with that tool, sometimes CDAS will prompt you with these messages just letting you know how things work. And so in the case of this tool, you're going to want to hold the shift key down, and it will automatically change the ranges in the plot of the spectrum view to give you a better view of what the plot itself actually looks like. So that'll just change the X and Y axis limits. So we'll go ahead and drag this slightly over here. And we'll give it a second. Oh, here. We're going to want to change the filter with that first, though. So we're going to take off some of these layers that it's automatically included there so that we're only looking at a plot of surface reflectance, and that's the RRS value. So now that we've changed that filtering option using the filter button, we're going to click OK. And then we're going to just toggle over the image, and that will kind of gather and collect all of that spectrum data. So I'm going to go ahead and hit the Shift key, and that's going to change that Y limit to give me a better view of what the spectrum looks like. So we're going to go ahead and toggle kind of around this open water area. You can see that has a pretty distinct spectral profile. And then we'll toggle over here to look at some of this above ground atoll feature. And you can see how that differs as well. This just gives you a nice, really quick look at how some of those spectral features will differ. Sometimes it can take a second to collect that data and buffer, but we'll just go ahead and give it a second. And you can see here as we kind of toggle into these below surface benthic features, we'll get different spectral responses as well. And so this is just a really quick and easy way to go ahead and explore through an image to kind of see what type of spectral profiles you can expect from the imagery you've downloaded. And I think this is a really interesting example too, because we've got some very different coastal features here where we have open water, above ground, and then benthic features as well. So it's nice to see kind of the difference between those. And then from this work, you can kind of get a picture of what spectral profiles will look like for different types of coastal or oceanic cover. And with that, I think that's pretty much all the time we have for our demo. So I'm going to go ahead and hand things back over to Juan.
Well, thank you, Zach, for that great demonstration. And here we're going to summarize today's session in a couple of bullets. So remember that coastal-based applications for hyperspectral data include the retrieval of benthic substrates, particularly in shallow waters, and the potential discrimination of species based on the spectral signatures and cover of these species, but also hyperspectral data can be used to analyze water quality at higher spectral, potentially also higher spatial resolutions as well, depending on the sensor. Also, we saw through the Zach's demonstration how to access hyperspectral data, particularly from the NASA's Ocean Color Web data portal. And here also to remind you the different websites. And also we included here the website for downloading HYCO data in particular, or just for general information about HYCO, as well as the average data portal from our partners at JPL. Also remember that there are upcoming sensors like PACE and the new designated deliverables such as SVG, which eventually will provide for new venues for assessing coastal and ocean systems never attained before. So stay tuned for those.